So today we're going to be talking about scientific notation. Sounds kind of like science, but science is also the same language as math sometimes. You do science calculations, mathematical calculations in science. Scientific notation is something that transcends into science as well. Science uses it and math uses it. Well, what is it? Well, let's write that down. Our first and only vocabulary term today is scientific notation. In order to talk about scientific notation, you have to think about something we call standard notation. Standard notation is just the way we normally just write numbers. We write 1,000 as 1000. That's 1,000. 1,256,000. The way we write it, that is standard notation. The way we normally write numbers. Scientific notation is a fancy way or a mathematical way to write really big or really small numbers. So it's a way that we can write numbers that are really big or really small. A little bit easier than writing out a big, long number if it's really big, or a big, long decimal if it's really small number. Well, what does scientific notation look like? How do you know if something is in scientific notation? There's my little eyes, so this is what it looks like. Here's an example. 4.7 times 10 to the third power. That is a number written in scientific notation all together. In order to be in scientific notation, you have to have both parts of it. You have to have the decimal part, and you have to have the times 10 to the exponent part. And there's certain criteria that make it scientific notation. The first one is this first digit right here in front of the decimal. In order for it to be in scientific notation, it can be only one digit. And so it has to be the numbers 1 through 9 in front of the decimal. So only one digit in front of the decimal. If I had 12.7, that's not scientific notation because 12 is 2 digits. If it was 0.7, that's still not scientific because I have to have a non-zero number. So that would be all the numbers from 1 to 9. Yes? The other part that makes it scientific is because of the times 10 and the exponent. So it will always multiply by the number 10 to some power or exponent. In this example, it was 10 to the third power. It'll always be times 10 to the blank power. Again, so if it said 4.7 times 9 to the third power, that is not a scientific notation. It's always going to be the 10. So when you think of scientific notation, you can think of it as I'm going to have some number times 10 to some exponent. And in our case, in the example up above, my first number was 4.7 times 10 to the third power. The 10 always stays the same. The cool thing about scientific notation is that this exponent, it tells us everything we need to know about scientific notation. The exponent in scientific notation will tell us three things. The first thing it will tell us is if we have a positive exponent, we are going to end up with a really big number. If our exponent's positive, it's going to be a really big number. I will also have a video replay of these. If the exponent is negative, what do you think? What kind of number do you think it's going to be? Right, because our definition told us either really big or really small. So a negative exponent means that we will have a really small number. Positive exponent, it's going to be a really big number. Negative exponent, it's going to be a really small number. Don't need your laptop right now. And then the last thing, can I move up to here? The last thing that our exponent will tell us, the exponent tells you how many spaces to move the decimal, left or right. So again, a positive exponent means it's going to be really big. Negative exponent means it's going to be really small. And the number of the exponent tells me how many spaces to move my decimal. Okay, let's turn the page and let's do some examples. These examples today are all going to be scientific to standard notation. So basically, I'm going to give you the scientific number, and then together, your answer will be in the standard form. Just a regular old number, however big it is, however small it is. All right, let's look at number 1. 4.7 times 10 to the 6th power. First of all, is that scientific? I have one digit in front of the decimal times 10 to an exponent. We're good to go. All right, the first thing you need to ask yourself is about the exponent. Is my exponent positive or negative? Positive. So is my answer going to be really big or really small? Really big. So here's how we show our work. I'm going to write the number that we start with. Now, I'm going to have to move my decimal 6 times. I move it 6 times because my exponent is a 6. But I need to move it in the direction that will make this number be bigger than 4.7. So because I need to go bigger, am I going to move it to the right or to the left? to the right, and I'm going to move it 6 spaces. So it's no longer here in between. I'm going to go 1, 2, 3, 4, 5, 6. There's my new decimal. And I have to fill in zeros. If you notice, in this example, we filled in 5 zeros. Do not, I repeat, do not look at this exponent and say, oh, I'll just add 6 zeros. Don't do it. You will get an incorrect answer. If this was a test question, do you think you'd have an answer choice that had 6 zeros? Yes, you would. They would try to trick you to see if you pick it. Don't just add zeros. All right. So then when I rewrite my final answer, 4, 7, and I have 1, 2, 3, 4, 5 zeros. So 3 places make a grouping. So my final answer in standard notation is 4,700,000. That's it. So if you manually did 10 to the 6th power and then multiplied that times 4.7, you would get 4,700,000. Now, I know this number doesn't seem that big, but 4 million is a lot, right? They might use this. What if I wanted to measure the distance between Earth and the sun in feet? That's a lot of feet, isn't it? Even if it was miles. I don't want to write out this big, long number. I would get fancy and put it in scientific notation. So this is scientific notation. This is standard notation. Okay, let's do another example. All right, the next example. 5.047 times 10 to the 3rd power. Can I just add 3 zeros?
No.
No, do not do that. Will I have an answer that probably gives me that? That's one of the ones you'll probably be able to pick from on a test to see if you know it. Right. We have to move the decimal. So let's start with showing our work. First question we ask, positive exponent or negative exponent? Positive. So am I going to have a big number or a little number? Big number. So I need to move my decimal how many spaces? 3. To which direction, left or right? Right. So it's no longer here. 1, 2, 3. Ooh, did I have any zeros I had to add this time?
No.
Not at all. So in this case, my answer would be 5,047 because the decimal is at the end. So we've seen how it works with numbers when they have positive exponents. Let's see what it does with numbers with negative exponents. You're right. So let's look at this example. 7.21 times 10 to the negative 2 power. 7.21 times 10 to the negative 2. I'm going to get ready, show my work. 7.21. Now, positive or negative exponent? Negative exponent. What kind of number am I going to have? Little, tiny number, which means it's going to be a decimal. It's going to be less than 1. All right, so I need to move my decimal 2 spaces in what direction? 2 spaces to the left. So it's no longer here. 1, 2. I have to fill in 1, 0. So my final answer is 0.0721. So it's the same thing, I'm just going the other way now to make a little tiny decimal. Let's do one more example. Our scientific notation is going to be 1.035 times 10 to the negative 5. Am I going to end up with a big number or small number? Small number, very good. So I take my number that I was given. I need to move it. How many spaces am I going to move this decimal? How do you know it's 5? Yes, because the exponent is a 5. So it's no longer here. Do I need to move it left or right? Correct. 1, 2, 3, 4, 5. Fill in my zeros. Final answer. 0.00001035. Maybe a number that small might be the diameter of an atom. That's super, super tiny. It's actually smaller than that. But that would be an example of when you might want to use a scientific notation to measure something that is super, super tiny.